Okay, in this fourth video we'll be looking at some examples relating to sides of a triangle. Okay, here's the first example. Show that b plus a minus c all in brackets times c plus a minus b in brackets is less than or equal to c squared. Hence show that if a, b and c are the sides of a triangle, then that expression b plus c minus a times c plus a minus b times this a plus b minus c is less than or equal to abc, and what is the nature of the triangle if equality holds. Okay, you may want to start on this first. Now, to do this, to show that the left-hand side is less than or equal to the right-hand side, we mentioned this in the first video. It's easier to do left-hand side minus right-hand side is less than or equal to 0, or you could do right-hand side minus left-hand side is greater than or equal to 0. I think we should do the right-hand side minus the left-hand side is greater than or equal to 0. So let's, you can start with that. So we can go c squared minus all of this, b plus c minus a times c plus a minus b. If we show that that is greater than or equal to 0, then that would be, I think, the best way to go. Okay, so we'll just say that we want to show that that is greater than or equal to 0. So you can start with that, expanding the left-hand side. So we've got c squared minus, you want to expand this, so you've got bc plus ba minus b squared plus c squared plus ca minus cb minus ac minus a squared plus ab is less than or equal to 0. Of course, keeping your brackets there before you expand. See if there are any like terms, and there are, that can be cancelled. So the bc's can go and the CA's can go. So you've still got c squared minus, sorry, we've got minus, now we've got 2ab here, so it'll be minus 2ab, because it's minus the positive 2ab. Then we've got minus negative b squared, which is plus b squared. You'll have minus c squared, and there'll be minus negative a squared, which is plus a squared. So we've got that, sorry, actually, we should just not do that there. We should say, well, that is equal to this, which is equal to, now the c squared's cancelled, so it's equal to a squared minus 2ab plus b squared, which is equal to a minus b squared, and that happens to be greater than or equal to 0. So therefore, we've just proven that, that this expression here, sorry, I should start here. C squared minus b plus c minus a times c plus a minus b. We're just expanding that. So that is equal to this, which is equal to that, and that, which is equal to that, which is greater than or equal to 0. So therefore, we can say that, so therefore b plus c minus a times c plus a minus b is less than or equal to c squared. Now in the second part of the question, you have to show that if a, b and c are the sides of a triangle, then b plus, so we have to show basically that b plus c minus a times c plus a minus b times a plus b minus c is less than or equal to abc. Now, if we compare that to what we've got, this appears to be the same. This appears to be the same, but we have this expression a plus b minus c here. So we'll have to use this 3 times and replace, we can replace the b, we can replace the ABC with each other. Okay, so that we'll come up with this combination here of a plus b minus c as well. Okay. And you'll notice that this final inequality here is symmetrical in A, B, C, because you've got a B plus C minus A, then you've got a C plus A minus B, and an A plus B minus C. So each, like pronumeral, each side, well, A, B, C, is always being subtracted from the other two sides. So it suggests that we can start with this and replace some of the pronumerals, or replace all of the pronumerals. So if we start with this first expression up here, and we replace, so I'll call this equation 1. So using equation 1, we can replace A with a B, B with a C, and C with an A, and then we'll just see what we get there. So let's just start off with our first expression. So we haven't replaced yet. So we've got that one. I'll call that equation 1. Now we will replace the A with the B with the C, and so we're just writing out the first one. Then we'll replace the A with B, B with C, and C with A. So this will become C plus A minus B times A plus B minus C is less than or equal to A squared. I'll call that equation 2. And again, keep replacing. We'll place the C with an A, etc. A with a B, B with a C. We will get A plus B minus C times B plus C minus A is less than or equal to, replacing the A with the B there, B squared. So we now have all of the things that are appearing here. We've got B plus A minus C twice, C plus A minus B twice, and A plus B minus C twice. And the other thing that gives you the hint for doing this, we know that the final expression has these 3 terms. This one has the 2, so that's why we need to do the replacement thing with this. Do it 3 times, and then you'll end up doubling up to get all those, okay? So now we can, we can't add. We're going to have to multiply equation 1 times 2 times 3. Now, we can do that since A, B, and C are all positive. Okay? And also, since A, B, C are positive and the sides of a triangle, we know that when you add 2 sides of a triangle, it'll always be bigger than the remaining side. So that's why we know that all these expressions here, are positive. So we've got A, B, C are positive and they're sides of a triangle. Therefore, all of these expressions, B plus C minus A, C plus A minus B, and A plus B minus C are all positive as well. Otherwise, your triangle wouldn't close up. Okay? So if we're multiplying, we would get that B plus C minus A squared times C plus A minus B squared times A plus B minus C squared. So we're multiplying all these together, is less than or equal to C squared. Well, we can do them times A squared times B squared. Now taking the square root of both sides. Now we can do this because all these expressions are positive. So square root both sides, and we will get that B plus C minus A times C plus A minus B times A plus B minus C. Actually, before you do that, you can write that both sides are equal to that, and then if we square root both sides, you get B plus C minus A times C plus A minus B times A plus B minus C is less than or equal to ABC, which is as required. Okay? Now here, we will have equality if and only if, and we'll just see, one sec. So here we'll have equality if and only if A equals B. That's because if A was equal to B, then B minus A would be 0, and A minus B would be 0, so C times C would be C squared. Again here, we would have equality if and only if B equals C, because C minus B would be 0, B minus C would be 0, A times A is A squared, and here also these are all like symmetrical. Here you'd have equality if and only if A was equal to C. Okay, and in this one here, down the bottom, you will have equality. So with equality, if and only if A equals B equals C. For example, if if A is equal to B, which is equal to C, let's say C equals A here, then these become 0 and you get B. And if A equals B here, you get 0 there and you'll be left with a C. So we've got a B and C. And if B and C are equal to each other here, you'll get 0 and you're left with an A. So you're left with A, B, C. So therefore we've got equality if and only if A equals B, which is equal to C. And just notice in this question, it's really important that you need to state that A, B, C are positive, and also that the sides of the triangle would be positive, because here we know that we have a positive expression there and a positive expression there, therefore allowing us to take square root of both sides, also allowing us to multiply the expressions here because everything is positive, and also being able to take the square root of both sides without the need to introduce absolute values, okay? Since we know that, for example, if A squared is less than B squared, then that will mean that the absolute value of A is less than the absolute value of B, okay? Okay, this is HSC 2001 question 8A. This is just the first part of the question. I'll write up the second part of the question later. Show that 2AB is less than or equal to A squared plus B squared for all real numbers A and B, and hence deduce that 3 lots of AB plus BC plus CA is less than or equal to A plus B plus C all squared for all real numbers A, B and C. If you could pause the video and attempt the question and restart when you're ready. Okay, now we, to get this expression here, we'll just start off with A minus B squared is greater than or equal to 0, and expanding that perfect square, you get A squared minus 2AB plus B squared is greater than or equal to 0, and therefore A squared plus B squared is greater than or equal to 2AB, and then just writing it the way that the question's written. 2AB is less than or equal to A squared plus B squared. Hence you have to deduce this. Now if you look at what you're trying to deduce, notice you've got an AB and a BC and a CA, and you've got an A plus B plus C. This suggests that we use similarity here and we replace pronumerals. So we can replace the A with a B and the B with a C, and that will give us 2BC is less than or equal to B squared plus C squared. I'll call that equation 2. And similarly, if we replace the, here we replace the B with a C and we replace the C with an A, we will get 2CA or 2AC is less than or equal to C squared plus A squared. Call that equation 3. Now, if you look at these three and this expression here, it appears that they've been added together. So we're going to add equation 1 and 2 and 3. And we will get 2AB plus 2BC plus 2AC is less than or equal to, now you've got A squared plus A squared, which is 2A squared. Similarly, the B squared and the B squared, and we've got C squared and C squared. And we're just about there, almost, actually. We can now divide through by 2, okay, and we'll get that AB plus BC plus AC is less than or equal to A squared plus B squared plus C squared. Now, we seem to have a part of this. We need to, instead of having A squared plus B squared plus C squared, we need A plus B plus C. It has to be in that format, A plus B plus C squared. So let's just start with that right-hand side of the inequality. A plus B plus C squared is just squaring this, and you would get A squared plus B squared plus C squared, but you'd also get 2 lots of AB plus BC plus AC. Now, if you want, you can expand this on your own, but, you know, the A would be multiplied by the A, the B, and the C, and the B gets multiplied by A, B, and C, and the C gets multiplied by A, B, and C. Collecting like terms, you'd get this. Now, we want to... we're going to well, I'll call this equation 4. Now, if we rearrange this, I'm just rearranging, we would get A squared plus B squared plus C squared is equal to A plus B plus C squared minus 2 lots of AB plus BC plus AC. And now we're going to substitute that into equation 4. So substitute the A squared plus B squared plus C squared here into equation 4. you would then get AB plus BC plus AC is less than or equal to A plus B plus C squared minus 2 lots of AB plus BC plus AC, and then just rearranging, you would get, and adding the plus 2 lots of this to the other side, you get therefore 3 lots of AB plus BC plus AC is less than or equal to A plus B plus C squared. Okay? All right. That's that result. Now, in part 2 of the question, I'll just write that out. Part 2 of the question, suppose A, B, and C are sides of a triangle. Now, if A, B, and C are sides of a triangle, then they're all positive. We also know that when you add 2 sides of a triangle, that they're always larger than the third side of the triangle. Otherwise, the triangle would not be able to close. All right. So when they tell you that they're the sides of the triangles, these are the things that you need to speak about. Okay. We have a triangle. We know that the sum of 2 sides in a triangle has to be greater than the remaining sides. So we know that. So this is what we've got. Well, actually greater than or equal to, I suppose. If it's greater than or equal to, it would be a flat triangle, but it has to at least join. Okay, so we know that A plus C has to be greater than or equal to B, or similarly, we know that A plus B would have to be greater than or equal to C, or that B plus C would have to be greater than or equal to A. This is since for a triangle, so that this is because the sum of 2 sides in a triangle is greater than the remaining sides. And of course, we would have equality if B was equal to A plus C, or if C was equal to A plus B, and equality if A was equal to B plus C. The equality thing would apply if it was actually a flat triangle, in other words, just some lines sitting on top of other lines, okay? Now, we're trying to get this B minus C. If I rearrange these first 2, I would get that A is greater than or equal to B minus C, and if I rearrange this one, I'll get B minus C is greater than or equal to A. And if I just call these 1 and 2, and if I combine them, actually I want the inequalities to go both the same way, so I'm going to change the direction of one of them, or just rewrite them actually. I'll just fix that in a sec. Actually, I'll redo that, okay? Because I do want my I want the inequalities looking this way. So I've got that, oh no, I'll do it the same way. So I've got B minus C is greater than or equal to A. In other words, yeah, so B is greater than or equal to negative A. Sorry, that was a mistake. So in other words, I can write this as negative A is less than or equal to B minus C. Okay, now I can rearrange this one here, and I'll get A is greater than or equal to B minus C, or that B minus C is less than or equal to A. Now I'm going to call that equation 1. I'm going to call that equation 2. Now now I can put all these together, and I can say, well, therefore, negative A is less than or equal to B minus C, which is less than or equal to A. Now this is the definition here of absolute value. So this means that the absolute value of B minus C is less than or equal to A. Okay, because this is, when you've got this, it's the distance, it's like you're looking at something like this. If you just look at this over here, for example, if you have this inequality, it means that x is 3 units from the origin, and then that can be written as absolute value of x is less than or equal to 3, because x lies within 3 units of the origin. So it's a similar thing if you just think of it this way. This can be written like that, okay? And so therefore, if we square both sides, because we know both sides are positive, you get that B minus C squared is less than or equal to A squared, okay? So this is how we can explain why B minus C squared is less than or equal to A squared, okay? Now, Now we're trying to come up with this expression here that 4 lots of AB plus BC plus CA. What we can do with this is to get something like that, we can just expand this. Okay, so if we expand that, we would get B squared minus 2BC plus C squared is less than or equal to A squared. Similarly, if we replace pronumerals here, so similarly, by replacing pronumerals, we know that A squared minus 2AC plus B squared would be less than or equal to B squared. So here we are going to be replacing A with B, B with C, and C with A. Okay, now we've done this before, this sort of thing before. So, sorry, I've just done that wrong. So, I'll just fix that. So we've got C squared minus 2AC plus A squared is less than or equal to B squared. And here we've got A squared minus 2BA or 2AB plus B squared is less than or equal to C squared. Okay, so we'll just label these equations. I'll call that 3 and 4 and equation 5. Now we're trying to come up with this expression here. Okay, we can combine all of these. So we would get that if we're adding equations 3, 4 and 5, 3 plus 4 plus 5, we would get, and so if we add equations 3, 4, 5, we would get 2 lots of A squared plus 2 lots of B squared plus 2 lots of C squared minus 2 lots of, we'll just do them in order, AB plus BC plus AC, and that's all less than or equal to A squared plus B squared plus C squared. Oopsie. Now, if we swap sides, if we just, not swap sides, but rearrange this, taking this A squared plus B squared plus C squared over there and this over there, we would get that A squared plus B squared plus C squared is less than or equal to 2 lots of AB plus BC plus CA. Now, we'll need to go and do the substitution that we did earlier, that A squared plus B squared plus C squared is equal to, so we're going to replace, now, sorry, this is going to go over the page. So since A squared plus B squared plus C squared is equal to A plus B plus C squared minus 2 lots of AB plus BC plus CA, or we're going to sub that. I can just write sub. Substitute that into this above, into the above expression. So we can substitute that into there. Sorry, I'm just going to go over the page. Using the A squared plus B squared plus C squared with this, A plus B plus C all squared minus 2AB plus BC plus CA into this line above, we get this. A plus B plus C squared minus 2 lots of AB plus BC plus AC is less than or equal to that. And then just taking this over to the other side. So therefore we've got that A plus B plus C all squared is less than or equal to 4 lots of AB plus BC plus AC as required. Okay. Now we're just going to have a quick look at the triangle inequalities, and we're going to prove them. Okay. Now, the triangle inequalities are as follows, that absolute value of A plus B is less than or equal to absolute value of A plus the absolute value of B. And the other triangle inequality, this is that the two sides of a triangle when added together are greater than or equal to, that the two sides of a triangle, these two sides, when you add them together are greater than or equal to that third remaining side. And also, you can do this by subtraction, that A minus B is greater than or equal to absolute value of A minus absolute value of B. These are often used in complex numbers, okay? Especially this one here. Now, we can prove, so for any real numbers, this result can be proved if we use, so using the fact that absolute value of x is equal to the square root of x squared, we can prove these things. So let's start with 2 times the absolute value of a times the absolute value of b. That equals 2 times the absolute value of a times b, which will be equal to 2 times AB if AB is greater than or equal to 0, or it will be equal to negative 2AB if the AB is less than 0. Okay? Now, so now if we look at the reason I'm doing this is because we'll be looking at a plus b squared. Okay? So if we look at absolute value of a squared plus absolute value of b squared minus 2 lots of the absolute value of a times the absolute value of b. A squared plus b squared minus 2 times the absolute value of a times the absolute value of b will be less than or equal to a squared plus b squared minus 2ab. Reason is that this bit here will always be less than or equal to that bit there, depending whether, because you'd be subtracting 2 times something bigger here. If one of these happened to be negative, you'd end up with a smaller result here than you would here, okay? Which is less than or equal to the absolute value of a squared plus the absolute value of b squared plus 2 times the absolute value of a times the absolute value of b. Because it's obvious that this would be larger than that. Now, if we rewrite this here as a perfect square, we've got the absolute value of a minus the absolute value of b squared is less than or equal to, this is just the normal a minus b squared, which is less than or equal to the absolute value of a, it's less than or equal to the absolute value of a plus the absolute value of b squared. Okay, now because these are now all positive, we can square root all expressions, so therefore the absolute value of a minus the absolute value of b is less than or equal to absolute value of a minus b, and here we're using, when we square root x squared, it's equal to absolute value of x, okay? So we've got the absolute value of a minus it's the absolute value of the absolute value of a minus absolute value of b is less than or equal to the absolute value of a minus b, which is less than or equal to the absolute value of a plus the absolute value of b. Now this will always be positive, so I don't need to take the absolute value of the absolute value here. Okay? Now, so this left-hand inequality here, this bit, so this bit is true with equality. So it's true with equality if and only if a times b is greater than or equal to 0. And this bit of the inequality here is true with equality, so the right-hand inequality. So this is the left-hand inequality, this bit here is true with equality if and only if a is greater than or equal to 0. So if AB is positive, and this bit here is true with equality if and only if AB is less than or equal to 0. Because if you look up here, if AB here was positive, you'd get minus 2AB. And if AB here are both positive, that means A and B would be positive. You'd get the minus 2AB as well, and that's why you've got equality there. And if you look at this right-hand inequality here, you would only get equality if this AB here was negative, because a negative 2 times a negative here would give you plus 2AB, and that's why you'd have the equality with that right hand. So that's that right-hand inequality. And this is with the left-hand inequality. Okay? Now, if we replace B with minus B in the right-hand inequality, so if we look at the right-hand inequality, and if we replace, which is absolute value of A minus B is less than or equal to absolute value of A plus absolute value of B, and if we replace B with minus B, then we will get the following. A minus B is less than or equal to absolute value of A plus absolute value of minus B, which is absolute value of A plus B is less than or equal to absolute value of A plus the absolute value of B, which is that first triangle inequality here. So these are the triangle inequalities there. Okay. Now, and so if we look at that right-hand inequality, and if B is replaced with negative B, then A times negative B would have to be greater than or equal to 0. Okay, so therefore we've shown that this second one, the right-hand inequality, so therefore the right-hand inequality will hold if AB is greater than or equal to 0 as well. So therefore, right-hand inequality holds if AB is greater than or equal to 0 as well. Okay. We have to show that absolute value of A plus B plus C is less than or equal to absolute value of A plus absolute value of B plus absolute value of C. Starting with the left-hand side, we've got that the absolute value of A plus the absolute value of B plus the absolute value of C is less than or equal to, now we're going to break it up, less than or equal to the absolute value of A plus B plus C. So it's actually equal to that, sorry. So it's equal to that. And now what we'll do, we'll use the triangle inequality with this, which is less than or equal to the absolute value of A plus B plus the absolute value of C. And again, we will use the triangle inequality here with the A plus B. And we know that absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. So that's less than or equal to the absolute value of A plus the absolute value of B plus the absolute value of C. Okay, now that's all using this result. So that was all using the fact that absolute value of A plus B is less than or equal to absolute value of A plus the absolute value of B. That's that triangle inequality there that we're using. Okay, now in part B, you have to show that the absolute value of A minus B is greater than or equal to the absolute value of A minus C minus the absolute value of B minus C. It's actually the absolute value of those absolute values. Okay, now for this question we're going to be using the result that the absolute value of A minus B is greater than or equal to the absolute value of A minus the absolute value of B. Okay, so let's work with that. So I'll just move that up. Starting with our left-hand side, we've got absolute value of A minus absolute value of B. Now we're going to write that like this. So it's actually equal to the absolute value of A minus C minus B minus C, because we get A minus C minus B plus C, and the C's cancel. Okay. So we've just rewritten absolute value of A minus B to include this C term because we're supposed to show that this applies. Now we can say, well, that is, now we can use the inequality thing here, that is now therefore less than or equal to, using this result, the, oops, sorry, I've just written that result the wrong way around. Actually, no, I haven't. That's the result. Absolute value of A minus B is greater than or equal to that. So therefore, that is greater than or equal to, now we can split them up, A minus C minus the absolute value of B minus C. Okay, which is the result that we were trying to prove. Okay. Actually, going back up here, there is an absolute value sign there in the rule. So can you also fix that up here, that there is an absolute value around the absolute values there. So make sure that you learn them that way. Okay. So these are absolute values as well. Okay, that's the some inequalities with triangles. Okay. For example, with inequalities, show that, sorry, not show then. So show that sine of alpha plus beta is less than or equal to sine of alpha plus sine of beta. and under what conditions will equality hold. So let's start with this left-hand side. So the absolute value of sine alpha plus beta is less than or equal to, now we can expand using sums and differences of angles. So it's, sorry, it's not less than or equal to, it's actually equal to. So that is equal to sine alpha cos beta plus cos alpha times sine beta. Now that is less than or equal to, using the triangle inequality, sine alpha cos beta plus cos alpha sine beta. Now that is equal to, we can split these up, that's equal to absolute value of sine alpha times cos beta plus absolute value of cos alpha times sine beta, which is less than or equal to absolute value of sine alpha plus absolute value of sine beta, since we know that absolute value of cos theta is less than or equal to 1. Because if you look at a cos curve, the values go between 1 and -1, and so therefore this will be less than or equal to, so for example, you might be doing sine alpha times a half. The maximum that this will be is 1, so this expression here will be less than this. Okay, this will always be less than that. Again, this cos alpha might be 0.9 or 0.1 or something like that. The most it could be would be 1, so that expression here is less than or equal to that. And so therefore we've proven this equality. Now, this inequality, sorry. So here equality will hold, so equality, so the conditions where equality holds, equality will hold if alpha or beta, and beta are, you'd need, for example, we've got here 2 pi and 0. So if alpha and beta are multiples, or are a multiple of pi, then equality will hold, okay? So if alpha and beta are not multiples of pi, they will be less than 1, okay, and therefore therefore equality will not hold. So if alpha and beta are not multiples of pi, then equality, then cos alpha and cos beta will be less than 1, and then equality will not hold. Okay, just clarifying something here. Equality will hold if alpha, actually only one of them needs to be a multiple of pi, if alpha or beta are multiples of pi, because if they're both multiples of pi, then what will happen is that if I look at the sine curve here, okay, and this is my cos curve here, if they are both multiples of pi, the alpha and the beta, then alpha and beta will both be 0, okay? But if just one of them is a multiple of pi, then you get 0, for example, for the alpha, but the sine beta will just be the same as the sine beta there, okay? So it's only if one of alpha or beta are multiples of pi.